Hello, Eastview Chemistry. Here we go with our first shot at distance learning. Before we talk about gas laws, just a reminder, you should have watched the kind of the intro to how we're going to do things, but we'll at least initially start with a little bit of PowerPoint lecture stuff and a few questions every day. And this week we'll just get our feet wet, knowing how we're going to do stuff. A little bit of math starting tomorrow with the gas laws, and then maybe we'll try some quizzing and stuff next week. We're going to hold off on the solution exam until we make sure everybody is comfortable with our online learning, and then we'll tackle that as need be. Anyhow, our next unit that we were going to start after the solutions exam was this gas law unit, and talk about gases as a phase and what makes them special. And so today is just going to be a short introduction to reminding you of the gas phase and some unique properties of the gas phase. And then tomorrow we'll start the math. When we do start the math, and there will be stoichiometry with this, if you for some reason have forgotten or can't find your cheat sheet for quizzes for everything that we're doing, I have put one up on Schoology, so you can just go to, I think it's PT 1819 or whatever, periodic table from our last adjustment, which was a year or so ago when we found some things to fix. Anyhow, let's talk about gas laws, all right? And gases. And here's some of this stuff should be a reminder, we hope, of early in the year stuff. Gases are composed of particles that are moving around very fast in their containers, okay, if there is a container. But again, they're the farthest spread out of all the phases. They move in straight lines unless they collide with one another and bounce off, or whatever they're encased in, whether that would, some sort of container, a tire, scuba gear, if you think of the scuba tanks or the oxygen tanks that they use in hospitals and stuff along that line. Okay, snapshot of these particles in a gas will reveal that there is mostly empty space. Anyhow, and again, gas is the only phase that can be compressed, and that's because of all the distance in the particles being that far apart. So you can compress it. Now, you compress it too much, and it will phase change back down to a liquid, and we'll see that as we really get into the math and stuff. But that is, again, the idea that if you think that solids were basically locked and just kind of moving in space, and then the liquid phase comes in as you start breaking some of those intermolecular bonds and start loosening things up, and the particles are moving faster and they're getting farther apart, and so they bring some fluidity to it. And then gases, of course, is basically, as we're going to see through this, that the particles are how should we say, so far apart, they're acting individually. And it's mostly empty space with these particles not interacting and no bonds together, okay? And let's talk about that compressibility, okay? You have two samples that you see below. Each has 8 nitrogen molecules and 2 oxygen. Oxygen in red and the nitrogen in blue, okay? The bigger the container, the farther the molecules are apart, because that is a property of gas. Those particles will spread out evenly to take up all the space that's available in whatever the container they are. The room of your house, the inside of your car, whatever it might be, okay? So you can see in the smaller container, the air sample is compressed and the molecules are closer together. That just, it's not changing the amount of the gas, but it is changing the pressure in some extent. But you can compress. You have the same molecules, just in a smaller container. Okay, and that gets us to pressure. And this will be a main focus of what we're doing there. Pressure is defined as the force the gas exerts on a given area of the container in which it is contained. Essentially, how often are the gas particles hitting the side of the container? So if you've pumped up your bike tire, your car tire, or something like that, and they give you a certain number in PSI, pounds per square inch, that gives you the idea of the force in a given area. That's one measure of things. Blood pressure is, again, a measure of particles bouncing off the walls of the vessel. Okay. You know, you've maybe shaken up a can of soda and then quickly open it so the stuff comes exploding out. You've increased the pressure because you've got them hitting the side of the container more often. Okay. So that's pressure. And unfortunately with pressure, there are many units in many different science fields, meteorology, etc., that happen. We're really going to use two, and that's the atmosphere and the kilopascal. Okay, those are the two that are most often used in chemistry. And kilopascal is what it sounds like. It's metric. There are 1,000 pascals in a kilopascal. You may run across in reading or some of the questions we do or work we do or whatever, as we have some daily questions to answer as opposed to having a packet to hand out. Torr would be one. Millimeters of mercury is one that's often can be used in meteorology, or inches of mercury you might hear when they talk about barometric pressure in the weather. Pounds per square inch we already talked about. Okay. So that's just giving you that idea. Okay. On your cheat sheet, if you look at it, you've got under pressure a number of different values that allow you for dimensional analysis to go between different pressures. Okay. 1 atmosphere is 101.3 kilopascals, is equal to 700 millimeters of mercury. Is equal to, I think it's 14.7 psi. I'm not sure, it doesn't matter to us. So as you can see by the math here below, then if I knew that I had 0.89 atmospheres and I wanted that number in kilopascals, then my conversion factor is there's 101.3 kilopascals in every atmosphere, and then the atmospheres cancel out. So 0.89 times 101.3 is about 90 kilopascals. Okay. All right. So you will have to do some converting and just know where those standard, these are called standard pressure values. Okay. And we'll talk about standard temperature values when we really get into the math tomorrow. Okay. Factors affecting pressure. One thing about gas is we'll see in the math, it's very linear. Okay. And there are different things that affect pressure and affect the behavior of a gas and its compressibility and stuff. One is the amount. If you have a container, the more particles you have, the more moles of gas you have in that container, the more times it's going to collide with the side of the container, and that's going to be a higher pressure. Okay. If you release some of that gas, so you remove some of the moles, get rid of some particles, you're going to reduce the pressure because you're going to have less particles. Pounding on the side of hitting the side of the container, and so the pressure will go down. And again, just a reminder that everything we do, starting with our math tomorrow, amount is always in moles. So anytime you might be given the grams of a gas, make sure you change it into moles. Volume is another, and we saw that with compressibility. If you increase the volume, you will decrease the pressure because you're now giving those particles more space to move in a larger area. So they're going to be hitting the side of the container less because there's more container to run in. You know, there's more container, so they're not going to hit it as often. Whereas in our picture of compressibility, if you decrease the volume and have a smaller container with the same amount of gas, then you're going to increase the pressure because now you have less container surface area, so the gas particles are going to be hitting it more often. And then temperature, remember temperature in chemistry is defined as average speed of the molecules. And so if you increase that speed, if you heat something up and then go faster, then they're going to hit the walls of the container more often. And so your pressure is going to go up. If you cool something down and those molecules slow down, then you're going to hit the sides of the container less. And so that pressure is going to go down. Okay? That's really our basic stuff. Now, where we're going to go tomorrow is start looking at these relationships. Now, they are all interactive. So you really have four things. You have the pressure, you have the volume, you have the temperature, and you have the number of moles, the amount. And they all work in concert together. But it's hard to design experiments that allow you to have four variables. And so we're going to break them down into a couple at a time, pressure versus temperature, and what kind of relationships do they have. And again, I'll preview tomorrow's math by saying that gases behave linearly. So they're either going to be just straight indirect or direct relationships, or sometimes indirect is known as inverse. Okay, so pressure and temperature is one comparison. Pressure and volume is another comparison. Pressure and amount is another comparison. We've already talked about those in factors that affect. Okay, but then also you can compare temperature and volume. You know, how does the change in temperature affect the volume? How about volume and amount? Okay. And when you're comparing those two, you're considering that the other two are constant. Now, the one that's always easy to hold constant is the amount of gas, the number of moles. The others that aren't as easy necessarily to hold constant are the volume, pressure, and temperature, but they behave so well that you can consider them held constant. Okay. All right. So that's where we're going to begin tomorrow. Now, there will be some questions after this as an assignment that you should go do. Just basically, it's basically doing packet work online. Please do that assignment so that if there's any questions that come up, you can ask those. Also know, as I mentioned, and I will have in our updates, I'm going to have 3 office hours a day at different times of the day. I would prefer for the chemistry folks to chime in on the second office hour so that we're all kind of, anybody asking questions, we're all together kind of covering the same questions, and we can answer similar questions for multiple people. And more details will be coming out on that on Tuesday and stuff. We're not going to rush right into that on Monday. That doesn't mean you can't go to office hours 1 or 3 and ask me questions. I'll gladly take those questions, but it's just that I'm trying to gear my courses to all go towards one time of the day so that we have more people having questions on the same material. Anyhow, that'll do for today on gas relationships. Take care, stay healthy, and we'll talk to you soon, Lightning.